Mount Etna erupted again, but this time what tore out of the crater wasn't lava, ash, or anything the mountain has produced in living memory. Witnesses described a surge of bright, almost electric material pouring from the southeast vent, glowing with a color that didn't match basalt, andesite, or any volcanic glass on record. For the first few minutes, geologists watching the observatory thought the cameras were glitching. It caused chaos. But the readings held and the confusion deepened. Lab tests would later confirm what the field teams already feared. Whatever Etna released today should not exist on the surface of this planet. The eruption. The eruption began with a roar that swept across the flank like a rolling shockwave. Within seconds, a pyroclastic surge tore downhill at nearly 140 kilometers per hour, fast enough to erase anything in its path. The ground had already been scorched by weeks of low-level activity, but the new burst added a level of force and heat that seasoned researchers struggled to describe. This wasn't routine behavior. This was something closer to a tectonic scream. Scientists were quick to label the event a paroxysm, but even the term felt inadequate. Paroxysms are violent, yes, but this one carried signatures no one could match to existing geological patterns. More alarming, Etna's internal geometry, mapped through satellite interferometry, had begun to resemble the state it held 7,200 years ago, just before a colossal flank collapse triggered a tsunami across the Mediterranean. That ancient disaster was powerful enough to alter coastlines. Now, similar conditions appear to be rising again from within. Whether this was a subtle warning or the opening chapter of something far larger, no one could yet say. Ash coated every rock, tree, and instrument as the first field team pushed toward the southeast crater. The ground remained dangerously hot from the earlier surge, and their boots sank into the patches of softened soil still steaming with trapped gases. Every breath carried the harsh tang of sulfur. The equipment malfunctioned almost immediately. A thermal camera, mounted on a tripod warped from the heat, managed one final coherent image before its lens fogged and its internal circuits shorted out. The last frame, a blinding blast of thermal radiation, was timestamped exactly 3 minutes before failure. The climb into chaos. Above them, a drone traced a shaky path along the edge of the glowing flow. Its rotors fought severe turbulence while relaying jagged fragments of footage. Then the signal cut off mid-transmission as the drone vanished into the rising plume. The lost footage lasted only 12 seconds, but it became the sole surviving record of the flow's early behavior. Progress toward the crater felt like walking on a living fault line. New fissures opened without warning, venting plumes of scalding vapor that rattled helmets and microphone housings. Radio chatter flickered with static. Visibility dropping. Thermal spike just doubled. Confirm? Are you seeing this from the control room? Each team member carried a specific loadout: sampling kits, batteries, spectrometers, and GPS beacons. Back behind the safety perimeter, the crew clustered around a makeshift workstation, reviewing the salvaged footage. The drone's final transmission showed the glowing flow splitting, branching like a river under stress, before a blinding flash swallowed the image. Whether the sample would survive analysis was uncertain, but the mountain had changed, and the scientists knew their methods needed to change with it. The lab panic. Inside the mobile lab, the technician removed gloves that had warped into uneven ridges from heat exposure. His knuckles were raw from friction. The sample vial, still warm to the touch, emitted a faint ultraviolet shimmer only visible when the lights dimmed. Instruments lined the counter: spectrometers, Geiger counters, and a scorched thermal probe. Readings blinked, froze, then flickered again. Under ultraviolet light, the material fluoresced intensely, unlike any known volcanic compound. When the gamma detector activated, the needle snapped to its upper limit and stayed pinned, warning lights flickering in a frantic rhythm. The technician rechecked the calibration. He ran a second probe, same result. Next came the melting test. Even under extreme induction heating, the fragment refused to liquefy. The furnace climbed past 1600 degrees Celsius, well above the melting point of known silicates, yet the sample only shimmered with a rippling blue sheen. Protocol demanded a witness, but the backup analyst was still outside repairing a corrupted data uplink. Alone, the technician sealed the vial, labeled it, and flagged it for immediate transfer to the main laboratory in Catania. A debate erupted on the radio. Some urged immediate shipment to the INGV's primary facility. Others questioned the readings, suggesting contamination or instrument failure. Then the technician spoke, his voice rasping from ash exposure. "I've never seen numbers like this. Not here, not anywhere." By dusk, the sample was locked inside a reinforced case and loaded into a transport van bound for Catania. Encrypted messages spread to partner labs across Europe. The mystery wasn't solved, it had only widened. A mountain out of rhythm. Etna has always lived at the crossroads of danger and routine. Its slopes support villages, vineyards, and families who've rebuilt more times than they can count. For scientists, the volcano's typical products, basaltic lava, sulfur gas, and glassy scoria, form a familiar baseline. Even dramatic fountains and ash plumes fit comfortably inside decades of recorded patterns. But today's eruption cracked that familiarity open. The data they didn't announce. At the INGV lab, X-ray diffraction returned patterns that didn't match any known terrestrial mineral. Berlin's geochemistry team detected rare earth elements in concentrations far beyond what surface magmas can carry. Paris recorded lattice structures that resemble high-pressure phases found only deep in the mantle. Each lab questioned its own results. Each ran the tests. Each returned the same unsettling numbers. Outside the scientific sphere, confusion spread across the villages on Etna's flank. Civil defense advisories contradicted each other. Some households evacuated immediately, others refused, anchored by generations of endurance. Rumors raced through town squares of new minerals worth fortunes, of government officials downplaying the risk, of scientists themselves unable to explain what they'd found. Inside the observatory's control room, the real alarm was hidden in the data streams the public never saw. Synthetic aperture radar showed asymmetric deformation on the volcano's southeast flank, values that exceeded thresholds set after the near collapse of 2002. A second data packet from atmospheric satellites revealed a persistent subterranean heat zone mirroring the same unstable sector. The conclusion no one wanted to reach. The risk of a flank collapse, an event capable of sending millions of tons of rock toward the sea, was no longer hypothetical. A restricted memo circulated among senior officials. Thresholds exceeded, persistent deformation confirmed, immediate protocol review recommended. Civil defense vehicles waited for orders that didn't come. Analysts watched their screens, waiting for the next spike. Communities waited too, caught between routine, fear, and the uneasy knowledge that Etna's behavior had shifted into something unfamiliar. No one knew what would happen next, but all agreed on one thing. Whatever erupted from Etna today marked a turning point. And with more satellite data still classified, the mountain's next move remains a mystery. Make sure our channel erupts by hitting that like and subscribe button, and follow for more content like this.